Good. All right. Hi, everybody. My name is Lovro. I've been working on a project called Klor together with Sung-Shik for the past, let's say, 6-7 months. And today I'm going to tell you a little bit about it. I only have 20 minutes, so I'll try to give you a taste and go over the major ideas we have in this language. Sung is sadly not here today. And a small note for the reviewers that have actually looked at the Klor paper, it's completely different now, right? So everything is new, everything's changed. So just unlearn everything you know. All right, so let's start off with Clojurian and Lisp. So how many of you, just a quick show of hands, how many of you have heard of Lisp? Nice. How many of you use Lisp? Use. Boo. Okay, how many of you know about Clojure? Again, okay. So how many of you have used Clojure? Okay. All right, so our idea was, so I'll say a little bit later about why Lisp and why Clojure, but our idea was to take Clojure and combine it with choreographies. We all know what this diagram is. And what do we get? We get Klor. So Klor, in a sentence, is our domain-specific language for choreographic programming embedded in Clojure. Now you can see this little prism over there. This means white light is coming in, dispersion happens. That's projection, right? Choreography comes in, disperses into its projections. All right, so now why did we choose to create a new language? So basically, Choral has core, chorus, all of these library level approaches have shown us we do want to combine choreographic languages on top of a mainstream language. Now what I don't like is, number one, I don't want a custom toolchain, and okay, some of these approaches get rid of that, but I want more control. I want to customize the syntax, I want to have custom type checking, I want to have custom analyses, I want to do lots of custom stuff. I don't want to be constrained to the interface that the language gives me. And the only language that can give me that is, of course, Lisp, right? There's nothing else that comes close. So that's where we're going to go. So that explains sort of the first part. So basically, I need very good metaprogramming support. One other thing that I get from Lisp is the interactivity and so like a really nice fluid development cycle. And I'll showcase this a little bit later in a quick demo if I have the time. And of course, all these Lisps are usually functional programming kind of style. So that's a nice thing. Clojure specifically for a couple of reasons. Number one, there's the JVM. So Clojure is a hosted language. It sits on top of the JVM. It's a Lisp for the JVM. So we basically just steal all of the ecosystem, steal all of the interoperability. I don't need to implement any libraries. I'm happy. Concurrency, this concurrency support in Clojure is immaculate. It's amazing. So it's got first-class immutability, basically immutability by default everywhere. It's got high-quality persistent data structures, and this is just a natural environment for a concurrent setting such as choreographies. Finally, tooling. Of course, I would tell you just use Emacs, right? There's no other editor. But the thing is, lots of people use different tools, so we just inherit and import all of that from the existing Clojure ecosystem, as well as from the existing JVM ecosystem, right? So you have profilers, debuggers, whatever you want, you can get it. All right, so quick 1-minute Lisp crash course for those of you who are rusty. Just quickly so you can actually follow the Klor code I'll show you later. So let's go from left to right. This is a list of integers. This is a vector of characters. This is a set of keywords. Keywords are a special kind of symbol. This is a map of keywords to integers, right? Four fundamental data structures all built into Clojure as literals. Amazing. Huh? Yeah, this is not your grandfather's Lisp. Now we're in 2024. All right, here's a function definition. Notice that Clojure code is literally just a bunch of lists, right? Code is data, data is code. So this is a factorial function. Takes a single parameter n. If n is 0, you return 1. Otherwise, you multiply n by the recursive factorial of the decremented number. So quite a simple, straightforward definition. You'll notice everything is sort of compositional, very uniform, prefix notation, all that stuff. Here's a higher order lazy example. This is a lazy list of an infinite sequence of integers, and this is just going to filter the list for all numbers that are divisible by 5. And here's the cool thing about Clojure, seamless interop with Java. Any Java goop that I need to interoperate with whatever service I can find, I just do it like this, right? So this is calling a static method of the local date, and then on that object that it returns, it's calling a method getDayOfMonth. Super easy, super straightforward. Right, now we jump into Klor. And the entry point of Klor is the def core macro. So this is a closure macro that we wrote. And the important part here, so that the stuff that I want to highlight is basically this macro completely expands at compile time. It's a compile time computation. And the macro basically performs projection. So unlike some of these approaches that we've heard about today that do projection at runtime, we do it completely at compile time. We're basically doing what Coral would do, but without the custom toolchain. We're just doing it by hooking into the closure compiler, right? So you could call this projection as a macro, if you need a catchy title. Another cool thing that we get from support for macros is that I can just reuse macros inside of Klor. All of the standard closure macros that I have, I can just reuse them there. So another cool thing that we have is a lightweight type system, and I'll talk about the exact types, what they are. Right now, it's not really important. Don't focus too much on the syntax. Just let your eyes glaze over just to get a feel. And then we have the kinds of expression that you can actually write in Klor. That's what comes in the body of the dev core. So basically, the ... is everything you get from closure. Let, do, if, whatever you want. And then these over here, 6 specific operators are Klor specific, right? And I'll explain what these are just through examples. We're not going to focus too much on very technical stuff. The reason I need a lightweight type system, right, maybe one thing I should mention, closure is dynamically typed, like every Lisp. And what the type system gives me, I guess this is a little bit unusual for a DSL embedded in closure. This is a type system that's running as part of the macro expansion, right? And it's completely just location-based. And all of the values that are still, in closure, they're dynamically typed. This is only telling me something about the locations, right? So I don't have an int at A. I just have a thing at A. Whatever that thing is, you decide. Another cool thing that the types allow me to do is multiply located values. So I can have choreographies as values. I can have choreographic tuples. We'll see more in a second. All right, so let's dig in. A taste of Klor. Here's a really simple choreography, no complicated behavior. To break it down, the choreography is called Simple 1. This is introducing a vector of roles. This is your current role context. You have access to A and B. Here's the signature of the top-level definition. If you're used to Haskell, this is what you would write normally, right? Top-level definition, and above it you have the signature. This means it's a choreography returning a B. Everything that would come before B would be the input parameters, which in this case there are none. So these are the value parameters. So there's the role parameters and the value parameters. In this case, what's happening, A is just going to be printing hello, and B is just going to return 1, 2, 3. Okay? So dead simple, no communications yet. Now we move on to communications. Now you can see what Fabrizio foreshadowed a little bit earlier in the day. So we're taking an X located at A and returning a thing at B. And how do we come up with that thing at B? Well, we're moving the X from A to B. And this is the kind of cute stuff I can do when I have control over the syntax. There's no ceremony. This is literally all you need for this choreography is written here, and there's no cruft anywhere. And now we get into the sort of a little bit of a novel thing, is essentially, well, we've heard already today at least 3 or 4 times. It's actually kind of amazing that people are converging onto the same ideas. So we have the idea of replication, or I call them agreement types. So this is the double arrow, which shares knowledge about X from A to B. And now you have an agreement type where both people agree on the value of this thing. Okay? So to dig into that a little bit more, imagine you have a choreography called Maybe Inc. So the idea is to maybe we will increment an integer. Again, we have A and B. So we're taking an X. This is a small typo. There's not supposed to be an X over here. But basically, A is going to flip a coin. And depending on the outcome, it's going to share the result with B, who is then either going to increment an integer that A sends to it, or it's going to print nothing. Okay? And the cool thing about this, and I think Mako already mentioned this, is basically there's no selections, there's no merging. Knowledge of choice is basically just taken care by requiring that the guard of the conditional is an agreement type. And then all of the people involved in the agreement, in this case A and B, can participate in the branches. Otherwise, they cannot be in the branches. Another cool thing about having a completely custom sort of macro thing is that I control the error messages. So when something goes wrong, you actually get a really nice readable error message. And here I can report, if you use C over here, I would say C does not participate in the condition in the guard. Sorry, it would not be, some crazy message. Now the double arrow is really just syntax sugar for this primitive copy operator that you've seen quickly on that one slide. But not only can we share knowledge, we can also forget knowledge. And I think Maxime actually had an operator called narrow. So we are all sort of coming down to the same thing. So imagine you take an X and it's of agreement type from A to B. It's of agreement type with A and B participating, knowing about the value. You can actually forget that this X is of agreement type by using narrow, and this gives you a thing of the same value, but just located at a subset of the roles. And this is useful when I want to do, I don't know, some local computation. I want to forget the agreement. I don't care about it. I'm just going to do a local thing at B. Okay? In a lot of the cases, so we have this subtyping rule that allows you to elide this explicit ugly narrowing. So a lot of the times you can just write X, and Klor is going to figure out what to do. And then what's the relationship between the double arrow and the single arrow? Well, the single arrow is just a copy followed by immediate narrow, right? Copy it over and immediately forget the sender ever had it. Okay, so that's the semantics. Okay, now we go on to lifting. So far I've used this syntax sugar. I've just explained it. Now I'm going to explain what this syntax sugar is. I call these role expressions, right? So you start, the operator is just the role from your context, and then you have a thing inside. This is really syntax sugar for an operator I called lifting. And now this is not the same as the choreographic enclaves idea. This is actually just a convenient way of informing the Klor type checker how to lift all free names and any value literals appearing in the source code, what roles to lift them to. So this is just about, syntactic convenience. When I write print line nothing, I don't want to write print line at A, string at A, write it out a million times. I just want to say, within this little lexical scope, assume everything that's not annotated, just assume it's at B. Okay? So, and that's quite nice to see visually. So there's not a lot of verbosity in there. All right. This is another thing that I think Mako touched upon. So imagine, so we have our previous example with the solo increment where B was doing a solo increment on X even though it was of agreement type. Now imagine you have a function like this and you leave out the B, right? So what's going to happen now? If the above thing is syntax sugar for lifting of B, then the thing below is syntax sugar for lifting AB. And this is going to correspond to a concept that, so I call this concept a homogeneous code. This means that the inc over here is going to be interpreted as happening at both A and both B. And this is going to be an operation that will happen at both. And the assumption in Klor is that all of these functions that happen at both, at all participants, it has to be a deterministic computation, right? So if an agreement thing comes in, an agreement thing should come out. If you violate this assumption, then stuff is going to go wrong. Usually this is not such a big problem in Clojure because we have immutability almost everywhere. Persistent data structures, all this stuff, so it's completely fine. Another feature that I want to touch upon is the idea of choreographic tuples. So a lot of the times you want a choreographic procedure that can return multiple values at different roles, right? So imagine you have an exchange key procedure, choreography, that's just implementing the Diffie-Hellman key exchange. So the implementation over here doesn't matter, it's just doing some modular exponentiation, whatever. But the important thing is that once this procedure is done, both A and B should have a key, right? And that's what I can do with a choreographic tuple. So this thing over here is really just a choreographic pair, choreographic tuple. It's saying the first slot is at A, the second, element is at B. And I introduce it with my little pack primitive. And then how do you actually use this? Well, if you have a choreography called secure, that's going to call into exchange key. And notice how we call other choreographies. We are providing the role parameters to instantiate a definition with. So one thing I forgot to mention actually is that all definitions in Klor are location polymorphic by default, right? There are no role constants. To me, this concept doesn't even make sense, so I just go with location polymorphic everywhere. And every time you invoke another choreography, you explicitly say which role is playing which role of the target choreography. So if you do exchange key with a bunch of parameters, whatever, you get this choreographic tuple, and now you can use the unpack primitive to unpack it into two things. The first one is going to be at A, the second one's going to be at B. And then, okay, you can do some encryption in this case just with an XOR. It's completely a toy example. Okay? So that's another idea that Klor has, the idea of these choreographic tuples for manipulating multiple return values. Another thing is forced agreement. So in the Diffie-Hellman example, actually specifically, we actually have the case where it's a mathematical result of the protocol that the key will be the same at the end, right? But you cannot capture this if the only way of transmitting shared knowledge is using copy, okay? So what we've added is this agree primitive that forces agreement. It says, here's a bunch of expressions. They all need to be at disjoint roles. And this thing is going to be of an agreement type result, okay? And if you violate the assumption that these expressions don't actually generate the same value, things are gonna go wrong. We have a bunch of little compiler options you can enable for some dynamic checks if you want. But you can decide this on a per choreography basis, which is nice. And then, so how do we rewrite now our secure definition over here to work with this new thing? Well, now it becomes simpler. Now there's nothing to unpack. You just get a K. That's your key of agreement type. Maybe I haven't mentioned it, but we also have sort of, let's say, some type inference, right? I'm not annotating what type K is. There's a type inference procedure over here that runs. Sadly, it's not as powerful as a Haskell type inference. So one of the future things I'd like to do is to do a Hindley-Milner style type inference for this thing. That would be cool. Right. One thing to say, or maybe a couple of things to say about the execution. So you've written all of these choreographies. So this thing is actually this macro, the DefCore macro, is going to get expanded, blown up into multiple functions, right, for each role. So how do you actually interface with these projections from Clojure code, from standard Clojure code? How do you invoke into them? Well, you use a part of our standard, let's say, not standard library, but our runtime. You say play a role, and here you give a name of the choreography, and then something that we call a role configuration. Similar to the stuff you do in Chorus, you define like the transport, how do you send, how do you receive, you know. Here you can basically plug in your own functions, sockets, whatever you want. UDP, TCP, doesn't even matter. It's completely transparent. And you can provide arguments for that particular projection. The way that the arguments are actually projected is just sort of an erasure style, right? So if you're mentioned in the role, you get it. If you're mentioned in the type, you get that parameter. Otherwise, you're sort of erased. That parameter disappears, kind of like in Coral. Right? And another thing that's nice that we provide is a simulator just purely for local development. So you can actually simulate the choreography locally. And what's that doing is just invoking play role behind the scenes with a bunch of little virtual threads using Java 21, which is another nice thing. All right, let's see. We have, just quickly, just to show, let's see. I'll do one example just to show how it looks. And I will choose maybe the authentication example, because I wanted to showcase the difference between this. So this is the authentication example from the book. And there's a bunch of selections and stuff going on, right? It's not easy to read. There's also like this retry thing going on. And the server has to be involved in this retry between the client and the authentication server, which kind of sucks. With our new approach, so in Klor, the way you would write this choreography would be like this. So I've separated the authentication choreography itself that involves CS and A from the agreement that the client and the authentication server are establishing. And the nice thing is that you sort of, with these agreement types, you are reifying that there is, that an agreement was established. And once you have that agreement over here, you can actually share it with S, who is then either going to send a random UID, aka the token, to the client, or the client is just going to generate an error. So now this example is very nice and modular. No selections, no merging, no nothing. Actually, before in Klor v1, this is a big rewrite, I actually did have the idea of merging and selections, and it was horrible for macros and for the type checking. It does not play nice, and this approach is much more compositional, I would say. Okay, and I think that's all I have. So feel free to ask any questions.
Yeah, I think we have. I think we have just barely time for a very quick question, and while we ask that, I would call the next speaker to get the mic and everything.
Hi, thanks for the talk. It looks to me like you can only have a process play one role at a time in a choreography, whereas in full process polymorphism, the same process can take multiple roles. Am I misunderstanding something, or do you only have that limited form?
A single role, you can invoke multiple choreographies at the same time with different, placing yourself at different positions of the instantiated choreography. So no, one process can play multiple roles at the same time.
Do you need your microphone back?
I'll take it offline.
Yeah.
Okay. Also, for the sake of time, I think we should move to the next speaker. Thanks
right.
again, Lovro.
Thanks. Also, I forgot to mention, find us on GitHub and stars.
Get away. You are done.
Cool.